Good morning, everybody. So interesting to watch crowd dynamics happen in smaller crowds. You guys came in, you're super chipper as soon as the problem went up. Everyone's like turning and focused. I'm assuming you're still excited and focusing. Just before we get into today's class, I wanted to make sure to remind everyone I have office hours today. I'm calling an exam review session because we have an exam Monday, and it's topics that will be related to the exam is what we're going to be going over. But similar to regular office hours, I will be preparing some questions on topics that students are interested in. So whatever you tell me to ask a question, I can prepare a couple questions on that, and we can kind of work through it together. And if we have enough people, we'll split into the two rooms as we did last time. It's all in each task 125. I have two giant whiteboards, and so we can kind of split into two groups and work, and I can bounce back and forth. So hopefully you can make that if you have time this afternoon. Any questions? You guys sad that redox is not on the exam?
No, not at all.
Right.
We can't move the exam back a couple days.
Say again?
I'm outside, we can't move the exam back a couple days.
I don't think that's a good idea.
I think it's great.
Lennon?
What is office hours?
1 to 2:30?
Oh, you said, oh, it ends at 2:30. I thought you said
1 to 2:30 today. If you absolutely can't make those times and you still want to meet with me, send me an email, see if we can find some time for like a few minutes to answer any questions you might have. Alright. Part of the reason I decided to push redox back is I wanted to spend a little bit of time making sure everyone's on the same page doing this kind of a problem, that you're able to show exactly how it is you're doing this kind of problem. And then I thought it might be worthwhile doing a more complicated combustion analysis problem, since I don't think we did that in class. We've done complicated ones, but we haven't done it with oxygen, nitrogen, hydrogen, and carbon by looking at the mass of products. We've only done it by percentage in the products, so I wanted to go through that. So we have some solution stoichiometry, we have this today, and we have a combustion analysis. So I need everyone to be focused, to be on, and we'll try to be moving forward as efficiently as possible. So if you've answered this question, I think that there's two right after it. What is the number of moles of each ion that's dissolved in water, as well as the total ions that are in water? So if you've clicked this in, go ahead and work on those two questions as well. I'm going to give you guys another minute or so to work on those three problems. And remember that if I walk around, I want to see it written out in a dimensional analysis approach. Think about sig figs as you're doing this problem too.
Okay, so it's because we think about it. For one molecule, there's two K-bonds because it's the K2. Do you go from moles to moles of oxygen? So you have the 1 mole of iron, that's 4 bonds, then you have the 1 mole of K2, that's 4 bonds. You have 3 moles of iron.
All right, let's go ahead and talk through this. So what's our starting quantity here? Can I get volunteers? One person to answer each question as we go through. It's our starting quantity. Ashley? Okay, so you went up here in the text. This many grams of potassium sulfate. What's the formula for potassium sulfate? All right, hopefully you're familiar enough with the polyatomic ions. I can give you any polyatomic ion, which cannot be on your note card, and you'll be able to write out the formula for that because you'll know what charge the polyatomic ion, you'll know what charge the cation is, you'll be able to make sure you have the right ratio of those two to make a neutral salt. Sulfate is a 2-, we need 2 potassium plus. Okay? So can I have someone describe how we start moving forward with this problem then? Sarah?
Convert 78.4 grams of K2SO4 into moles.
And how do we do that? What conversion factor do we use to get from grams and mass to moles? Say again, molar mass?
The molar mass.
Okay, so what do I write here?
On the bottom, it's 174.259 grams of potassium sulfate is 1 mole of potassium.
Great. So this allows us to convert from how heavy it is in grams to how many of them there are in moles. Are we done? So how do we get from the number of potassium sulfates to how many there are in ions? Can I get another hand? Kayla.
1 mole of potassium sulfate is 2 moles of potassium.
Potassium ions? Okay. So when we say potassium, it implies the neutral element. So if we're talking about K+, we need to say potassium ion. So yes, we can do this. What does this tell us? What do we find out if we do this calculation? The number of moles of potassium ions. How does that help answer this question up top? Kayla, it can. You can use this approach. It's totally fine. And actually, we'll show in a second it's more accurate if we're talking sig figs. So how does this help us? How does finding this help us answer the question? Nice and loud?
You're finding the moles of potassium in the solution.
Okay, and then how does that help us answer the total ions?
You would have to do another thing for sulfate.
So we do the same calculations, and then we'd say for every 1 mole of potassium sulfate, there is also 1 mole of sulfate ions. So if we do that, 1 second. If we do that, how many moles of potassium ions did you find, Kayla?
0.9011.
Okay, can you give me a little bit more? Do you have more written out? Right, so we're going to highlight sig figs in a second. I wanted to include more digits, and then we'll figure that out in a second. Does anyone have more digits?
I got it. 0.9009577.
009.
577.
Okay, good enough for now. Moles of K+. And what would it be for moles of sulfate? Half that?
0.4504788885.
Okay. Moles of sulfate ions. Now if we know the number of moles of sulfate ions and moles of potassium ions, how do we answer this question? We can add them together. So if we're answering this question, we do not stop and round these to the appropriate number of sig figs, because that's not the answer to this question. We don't round until we get to the answer of a question, and we still keep the more accurate numbers laying around in case we need to do more calculations with them later. But we can tell ourselves, I know that I can only limit whatever answer I have going forward to 3 sig figs for each of these numbers. So if we add together those two numbers, has anyone done that?
1.35.
1.35
Moles of
K2.
More. So I want literally these two numbers added together. If we do that, what do we get?
Oh,
5.
1435.
Gail, can you say it again?
What?
Were you saying the number? 1 point.
Do you want the whole number or just
Keep going. You'll give me lots and lots of digits.
3, 5, 1, 4, 3, 5, 7, 6.
Okay, so I'm going to stop there. This is how many moles of ions we have. So let's think about sig fig rules. The first one was multiplication. We started with 3 sig figs. Our answer is limited to 3 sig figs and 3 sig figs, right? So that's the thousandths place on each of these two numbers. If we now do addition rules, we're limited to which has the least certainty as far as decimal places. Well, they both have certainty to the thousandths place. So where do we report this answer? We also report that to the thousandths place. So we look at this 1. Okay, that's the last thing we can do. So we report it. Do we round it up or leave it? We leave it. So that means that our final answer, if we do the addition way that Kayla did, is 1.351 moles of ions in solution. Jackson?
What I did was instead of having to take.
We're going to get there in a second. You're talking about doing all ions instead of separate.
Yes.
Okay, so I'm highlighting something because Kayla brought it up, and it's a good time to talk about sig fig rules. So if we did it this approach and we found the number of individual ions first, we end up with 4 sig figs in our answer. We end up reporting to the thousandths place. The other approach we could do is,
Well, you could just say instead of each K2SO4 is basically 2 potassium plus 1 sulfate. That's 3 ions total. You're
Great.
asking for the number of ions total.
pause. So in this calculation here, I think I saw a lot of people doing that as well, which is totally fine as well. We know how many moles of potassium sulfate we have. If we know how many of them we have, and we know that each one generates 2 potassiums and 1 sulfate, we could have 3 moles of ions for every 1 mole of potassium sulfate. That would give us this answer, this numeric value directly. What about sig figs? How many sig figs would we be able to report the exact same answer with the same precision?
No.
What would we be able to report?
3 to the hundreds.
1.35 moles of ions. Okay, so 2 completely valid approaches that give different number of sig figs based on application of sig fig rules.
Could you just stop before the 2 moles of potassium ion and the 1 mole of, say, get the moles and then do another calculation later? That's how the homework does it, a lot.
So,
On 10 gauge.
so you mean stopping right here?
Stop there, get that value, and then going forward after that. So they want you to stop at moles, you get whatever your moles are, and then they say, all right, you broke it apart, start going for piece by piece by piece later.
Yeah, and so the reason your homework does this is to make sure to guide you through the process. Scaffold your problem solving in case you're lost and you don't know where to go. That's why they have you report out multiple values in between. It's not because they necessarily want to see those numbers, but they want to make sure if you're not sure where to go, they're kind of guiding you through it. Does that make sense? And if you stop and report those numbers, if you were to report this number, if it asks you to report it, you do have to round when you put that answer into the answer box. That's your point?
No, I'm
Or one of the
asking,
things.
can we just, for the test, this is going to be directly related to the test.
Sure.
I did it the homework way. I stopped at moles, and I got the 3 sig figs, 0.451 moles. Then I went forward and multiplied it by 2 moles of K2, and then I already knew it was already 1 mole of SO4, so there's that.
So
value.
if you were to show this step as unit conversion, I would be okay with that. If you only have one of these 3 questions, right, because I asked you next, how many moles of each ion are there? If I was asking you all 3 of those, you would definitely want to stop. It would probably be useful to stop the moles of K2SO4 and then to do 3 separate calculations. Any one of those would be fine. But I think the major take-home that I have is I want you using dimensional analysis. I want you identifying what is this unit, how do we convert from this unit in mass to a unit in quantity, and then the quantity of the whole thing to the quantity of what is in it. Caleb?
Is there a preferred way throughout,
You mean out of these two?
out of the two ways, there's not.
No, so you're limited, you get slightly fewer sig figs if you do this approach, but I'm not going to ask you to do both and then say which one gives you better sig figs. Pick your way that's more efficient for you, that makes sense, and then go ahead and do that. I think the top one is faster because we only do one calculation. If you're asked all three of these questions, how many moles of each ion and how many total, then it's probably faster to do this and then add those together. But up to you. So this is the kind of thing you probably want to practice before the exam to make sure that you are comfortable doing one or the other and to do it quickly and setting up these types of conversion factors and using them. Any questions? All right, so our learning objectives for today. We talked a lot about dissolving a compound and how that's different from having a chemical reaction. You guys had a lot of drawings of water molecules associated around a molecule, and we want to think about that when we think about precipitation reactions versus ions dissolving. There's differences there between a chemical reaction and something dissolving. We're going to talk a little bit about naming of ionic compounds. You guys have done a lot of this in lab, so we're not spending much time on it, but I just want to pull out 1 or 2 points. And then we're talking about the concentration of ions and the number of particles in solution. And lastly, we're going to do a combustion analysis. So we're going to have to roll pretty quick to get to the combustion analysis. This is a question I had on one of these a long time ago. Let's make sure we're on the same page of answering this. So we just talked about potassium sulfate. Which one of these best represents a view of what that would look like? And note that the water molecules are not shown, but there's water molecules around all of these. You guys have the picture in your phones? Yes. On your computers? All right, I'm going to exit out of this for, well, I can't. Never mind. A couple more seconds. All right, closing out. All right, we're kind of split. We have one major answer, but we're not 100% certain. How do we look at this and decide which one of these? Talk to your neighbors. See if you can come to an agreement, a consensus of which one of these answers is right. It may be a major one, it may not be. Would someone who changed their mind be willing to describe why they changed their mind? About which answer they think is the most accurate representation. Kayla?
So, me and Angel said we thought it was C because it is like a strong electrolyte, so it completely dissociates. And then there's 2 K2s for one.
2 what?
2 K ions for 1 SO4 ion. So, yeah, C shows that.
Great. And so I wanted to catch one thing you said, and it probably was a mistake in the way you said it, but I want to highlight it because it's a common mistake that actually happens. A lot of people will say, that's a bad color, that K2SO4 will break apart into a K2 ion and an SO4 ion. What does this imply? It implies that they're bonded together, that there's a compound that has K2, like H2, right? Is that what happens? Not at all. So this diagram really helps us kind of visualize that every sulfate, remember we have 4 different oxygens with 2 negative charges. There's 2 potassium ions that are K plus each. So the way to write that is 2 K pluses there's 2 positively charged potassiums for every 1 2- sulfate. That's a very big difference. And keeping that in mind, if we visualize the molecule itself, and what is molecular is in covalently bonded, right? The sulfate is 4, 5 atoms that are covalently bonded together that do not separate. The potassium ions and the sulfate ions will separate. And there's 2 K pluses. Okay? So what's wrong with the one on the far right? The ratio is off. We have 2 sulfates for every 1 potassium. Here, why is this not accurate? B? They're not fully dissociated. If it's a strong electrolyte, we assume full dissociation. And then A is even worse than that as far as they're not dissociated at all. All right. So I want you to be able to take any salt. If we say it's a strong electrolyte, it dissolves fully. You should be able to describe that it breaks into 2 potassium plus ions and 1 sulfate ion that are aqueous, which means they're dissolved. If I ask you to do this and I don't tell you it's a strong electrolyte, I don't tell you it's fully soluble, how would we decide whether this occurs or not? Solubility chart. So I will give you the solubility chart on the exam. You have to go look at the solubility chart, say, would this dissolve or not? Is it soluble? If it's not soluble, we would probably choose to write no reaction. Nothing happens. It stays as a solid. All right, let's talk a little bit about naming. And I think this is, I don't know if I transferred this from the previous worksheet, so this is on last class's worksheet. I had a few questions together.
Will you be telling us whether it's 2?
I'm not telling you.
Well, in iron, I mean, like iron 2 or iron 3. It always would tell us how much charge it has.
A couple more seconds.
I know, right, so whatever, like with iron, it's different. So whatever the compound is, it's going to have to equal electrons.
Closing out. So we have about 1/5 of the class is correct. Why? Great. So iron's a transition metal. It can come in multiple different states. So if we say iron phosphate, that's useless. That name by itself is absolutely useless.
So you don't know whether or not it's iron 3 or iron 2 or iron what.
All right. What about this one? We have no idea with that last one. We need more information. What about this compound at the bottom?
Question on the last one, but I mean, obviously on this one, but wouldn't it be balanced if it's sitting up there?
Yeah, that's fine. That's what they have like on the
That information?
sim gauge.
Say what?
If you said iron phosphate, you would assume balance.
You can't assume balance. Balance with what? There's iron 2 is possible, iron 3 is possible. Which one is it? If you don't know which one it is, you can't say it's balanced.
So you can only do
Phosphate's
it after
gonna be
transition.
a 3 negative charge.
True.
So
But if it's paired with an iron 2, you're going to have a different number of them in the salt. And if you have an iron 3, you're going to have a different number in order to get a neutral salt. So that ratio is unknown until you know what the charge of that iron is. Which is why I wanted to spend a minute on in class today. All right. In this case, we can say with 95% certainty, or greater. Yeah, the first one you would never see this. But I would never want you to write that either, and so that's why I'm showing you from that side. If you are working with a transition metal, you do not know which charge state it is, and hence you can't balance a compound with the right number of negative charges and positive charges because you don't know what charge state it is. It's like saying it's a metal from group 1 or 2. How many phosphates are you going to have? I need to know what the charge is or else I can't figure out that neutral salt. So when we have a transition metal, it will always have in the name a Roman numeral, which tells us the charge of that ion. And now that we know it's iron 3 phosphate, could you guys write the formula for that? What's the charge of phosphate? PO4 3 minus. So if we have one iron 3 plus, then that would be the formula for iron 3 phosphate. What would the formula be for iron 2 phosphate? Could you figure that out? If it's Fe2 plus and we have phosphate PO4 3 minus, can we just do a 1-to-1 ratio of those?
No.
Okay, so we need to figure out what the right ratio is in order to get the same number of positive charges and negative charges. And those are going to be two different formulas. All right, let's move on to the next question, which I asked you guys specifically to try to calculate before. So I'm hoping that you guys are able to do this very quickly. I think this has been on the third worksheet it's been on. All right, spend 1 minute looking at just the first one and try to figure out how to answer what the concentration of ions is. Remember, we're talking about concentration, so use what's in the problem to try to figure out how to answer this quickly. And those units are millimolar. So 75 millimolar is 75 millimoles per 1 liter.
Okay. Oh, yeah. I thought you were asking something different.
If you were texting me at 10 and I was
Why
there.
two different problems? Did you just do it in one big equation? I see it.
Well, wouldn't it be? I kept dropping my iPad on my feet.
All right, so I said unpack this. 75 millimolar. Let's rewrite that as 75 millimoles per 1 liter. It's iron 2 phosphate, so what did we decide the formula is for iron 2 phosphate? Dawson? Like that? Great. All right, so the first thing we have to do is figure out the formula for each one of these, if they're ionic compounds. So that means in every 1 liter solution we have 75 millimoles of iron 2 phosphate. So can we go from the concentration of the compound to the concentration of ions? How do we do that? Rhea?
When you do molarity, it's like moles in a solution.
Yep.
Like 1 liter.
So it's moles in 1 liter of solution. I should have wrote solution here.
Yeah, it's like.
Convert it to what? We could, but we're trying to be as efficient as possible. What conversion factor have we just been using to figure out how the moles of ions relate to the moles of the thing itself?
Total number of atoms.
Total number of them. So for every 1 mole of Fe3, PO4 2, how many moles of ions do we have?
5.
So it's 5 times 75, 425? Is that right? Dang. It's a skill to try to learn to do mental math in front of 60 people. I haven't mastered it yet. No, I didn't.
I
Yeah,
do.
Mo?
So, what does the measurement of normal represent?
So milli, as in anywhere you see milli, always means 1,000. 1 times 10 to the negative third.
So it's 1,000 to the mole.
Yep. And so here in this example, the only thing I converted was moles, but I left the milli. So that milli carried over, and that's why that milli is still there. I didn't touch the times 10 to the negative third.
Was it in the question that there will be it's dissolved in 1 liter solution?
Nope. But it doesn't matter. Because what else did I leave out of this answer?
It doesn't dissolve.
And that.
Okay, so I also didn't touch the bottom, so that's probably what you're pointing out. It's not a number of moles. That's really important and a really big mistake that I just made, so thank you for pointing that out. Right, we're converting concentration, so we can convert the numerator from the number of moles of iron 2-phosphate to the number of moles of ions, but that doesn't change that it's a concentration, so it's out of per every liter of solution. And then we say, what about sig figs? How do we report this in terms of sig figs? We had 2 sig figs starting, it's all multiplication, so our final answer should be 2 sig figs, which is
380.
millimolar of ions. Okay? Do the same thing for all the other ones. Try to figure out which one has the highest concentrations of ions in solution. I'm going to give you guys another 2 minutes to do this. So we could either do 3.8 times 10 to the second, but this is, if I put a dot there, it's 3 sig figs. If I don't put a decimal there, then it's only 2 sig figs. Oh, you mean, no, for this one we are Okay, the caveat for this question, which Savannah pointed out, is I have written assume 100% dissociation for salts. If I didn't have that up there, would you be able to discount some of these right away?
Oh yeah.
Because they're not soluble. So the point of this question is not necessarily solubility rules, although that would be an additional layer that we could then go back and say afterwards, well, we calculated this many moles of ions, but they actually don't dissociate.
So
for now,
solution cannot exist.
So for now, assume everything dissociates completely. So we need to find the formula for each one, and then we need to figure out how many ions each one makes, and then what the concentration increases to. So I'm going to give you guys 1.5 more minutes. Alright, let's walk through this. Sodium, I think I have this for iron 2-phosphate. How many ions do we have for every sodium carbonate? Hold up your fingers. How many ions do we have for every sodium carbonate that form if it dissolves? Alright, Na2CO3, carbonate is 1 ion, and there's 2 sodium ions. So if we would have 3 times this concentration. With 2 sig figs, I got 250 millimolar. Does that make sense? All right. What about glucose?
That doesn't dissociate into ions.
But we have 6 carbons, 12 hydrogens, and 6 oxygens. Don't they dissolve? They do dissolve, but they don't dissociate. There's not a chemical reaction that occurs. Glucose doesn't break up when it goes into water. Like we drew last class, we have waters that kind of are attracted to it, which pulls it into water. So we have no ions formed at all, even though there are glucose ions, glucose molecules dissolved in solution.
Glucose ions.
All right. Perchloric acid. This is one of the 6 strong acids I said you need to know. So perchlorate is one of your polyatomic ions. Because I say the word acid, what do you know is going to happen? Tyler? Say again? It has a hydrogen that when it goes into water is going to be released as an H+. So how many ions are we going to form for perchloric acid? 2. Every perchloric acid is going to release 1 H+. It only has 1 hydrogen. It can't release anything more than that. And then this is perchlorate, one of the polyatomic ions I said you guys need to know. And the reason you need to know it is because it's part of perchloric acid. You need to be able to recognize that perchlorate in perchloric acid.
Yeah.
The last one, calcium hydroxide. How many ions does each calcium hydroxide make?
3.
Calcium is a 2+, hydroxide is a 1-. So calcium hydroxide generates 3 ions. And going back to Joey's point, 1 sig fig can either be shown like this, or this is also 1 sig fig in the bottom right corner, because those 2 zeros are not shown as accurate. If we had a decimal after the 300, that would be 3 sig figs. All right, so which one of these generates the highest number of ions in solution? The one that we can say with the most accuracy is our iron 2 sulfate. Let me put a twist in this, though. Which one of these has the highest concentration of particles dissolved in solution? Talk to your neighbor, see if it's the same answer, see if you choose something else. Couple more seconds, come up with the decision. Closing out. All right, we're 50-50. Talk to your neighbors about A versus C. 15-second discussion. A or C? A or C? All right, still open. Click in your decision. Final decision now. Closing out. Submit your final decision. Well, we honed in on those 2. That's great. Tyler, can I ask you to share what I overheard a little bit of your conversation? It was fantastic.
So in this case, you're asking for particles dissolved, not ions, so they can use glucose here.
Because glucose dissolves, every glucose ends up being a particle in water. It is not ionic, but it does dissolve. And so in this case here, if we're talking about which has the most things dissolved, even though we get 5 particles for every phosphate that are ions, it still doesn't come close to the concentration of the glucose that happens to be more in that case, right? So this is actually second semester. We're going to spend a ton of time doing calculations based on this. The way that we get the temperature of water, the freezing point of water to decrease, freezing point depression, is by adding more and more particles into it. The more particles there are, the harder it is for water to form ice, and ice expands, so a lot of times we don't want ice to freeze. On the roadways, we don't want it to freeze, so we add particles. We could add glucose, but we'd have to add a lot of glucose to get our roads not to freeze. We could add something that has a lot of particles that are ions that are lower molecular weight, and we can add less weight of iron to phosphate onto the roads, and we would get them not to freeze. You guys don't really have that problem here, but you know, in the rest of the country we have that issue.
Well, when we do, it just goes full blown banana pants.
Yeah, we just stay off the roads. That's what I heard. All right, so let's pause. We have 9 minutes left of class. I hate these 50-minute classes. I can't wait for next semester when we're doing 75 minutes. All right, so we have 3 different topics that we can work on. Focus. We need to focus. 3 topics. 1 is going through these and identifying types of reactions. 2 is solution stoichiometry. 3 is combustion analysis. All right, so all 3 are on the test. We're basically practicing all 3. So I want you to raise your hand for only one of them. Which one do you want to work on? We have 9 minutes, okay? First one, determining reaction, if it's what type of reaction it is. We're not doing redox. Okay, raise your hand if you want to do solution stoichiometry for the last 9 minutes of class. All right, combustion analysis. Okay. Let's do the combustion analysis problem. So flip over. It is problem number 10. Can I get someone to read the start of it? Someone read it out loud. Sam, can you read this one out loud for us, please?
No. Sam was found to be, no, I'm just kidding.
Okay, who wants to read it?
I'll read it.
Go, Brie.
2 graduate students were found to be making some white powders on the, on a weekend night. You hear rumors they were making ecstasy, aka E. So you requested an elemental analysis of the compound.
All right. I mean, there's a lot of student debt. There's actually a lot of graduate students that have made meth or E or other things in order to try to get over that. So, focus. Legit Wikipedia. You can Wikipedia that and get the answer immediately. So the question is how to make it and whether you want to make it. Okay. So we have the problem up and running. I want you guys to work together and come with a plan. Come up with a plan before you start it, and then go ahead and start the plan. Okay. So talk to people next to you. Come up with a plan. In about 3 minutes, we're going to come back together, and we're going to work on that plan together, but I want to make sure everyone's able to come up with a plan on their own, think through it. If you're totally lost, raise your hand, Sam and I can come around and help.
Oh yeah. That's really good.
All right, 30 more seconds. Make sure you have a plan written down and started on it, and we'll walk through that plan. right, let's bring our ideas back together, and let's think about how to approach this problem. Can I have a new voice that hasn't talked yet describe the approach, how we start this problem, kind of how we move forward? Tripty?
First, you find
A little bit louder, please.
define the mass of carbon from 335.4 milligrams using the dimensional analysis.
Okay, pause. Even before we find the mass of carbon, can we just cross any of these off the list? Aaron?
The first thing I did was eliminate any of the answers, but then all the elements that were produced in that drawing.
Great. So we know for a fact that we have carbon in our reactant. It ended up in carbon dioxide. We know we have hydrogen in our reactant. And we know we had nitrogen. Do any of these answers not have all three of those? And possibly oxygen. All right, so we know that they weren't making aspirin because we got nitrogen dioxide out of this. Okay? Once we do that, why is it important to find the mass of carbon in carbon dioxide? Why is that relevant at all?
Because in each of these, it doesn't have carbon dioxide in them, so you need to find this carbon is in each of them. So you have to know how much carbon is in them.
Oh, so you're going backwards. So you could start with all these, see if you burn that much, how much CO2 would it make? Totally legit. I think we're going to work backwards in class today since we only have a couple minutes. So if we work backwards, where did all of this carbon come from? Every single bit of carbon came from our initial sample that we burned. What about the hydrogen and water? All of that hydrogen came from this compound, and all the nitrogen came from that compound. All right, what about the oxygen? Did the oxygen all come from that initial compound? No. It came from O2 and from our compound. So that's going to be the tricky one to find. So if we find the mass of carbon in our product, that's the same as the mass of carbon in our reactant. Find the mass of hydrogen, same thing. Mass of nitrogen, the same thing. And those will all add up to less than 127 milligrams if we have oxygen in that compound. So let's work through this since we're running low on time. So we know that we have... So I'm going to work on this on the screen. Hopefully you guys are working on it too. I'll try to do it quickly, and I have a calculator, so we should be able to do this.
I'll keep my calculator ready.
Because I didn't touch the milli in milligrams, I just carried the milli through. All right, and then we have did I miss a step? I totally skipped a step. You see the step I missed? I just assumed that 1 mole of CO2 was 1 mole of carbon. I have to show that. That is a lot of points. Don't do that. Don't pull a Bailey. What did I have? 18.0. And then what's our conversion I need here for water? How many moles of water are in every, or hydrogen are in every mole of water? Did anyone do this for nitrogen? Already have the number for nitrogen? 7.61 of nitrogen. Okay, so here's the hard part, right? How do we figure out how much oxygen there should be? So we know we have 127 milligrams of the starting material, right? Minus how much nitrogen? 7.61 milligrams of nitrogen. Minus 10.429 milligrams of H. Are those the numbers you guys had as well? 91.41899 grams of carbon. What do we find? 17 point. I couldn't hear you, Josh.
54205
grams of oxygen, milligrams. So if we know how much oxygen we have, we know how many moles of each of the other ones we have, can we now figure out what the ratio is between them? So we need to go back from this. How many moles of oxygen is that? Did anyone figure out how many moles of oxygen we have?
I have 1.089
Millimoles? All right. So we're already 3 minutes past the end of class. But what we want to start doing is thinking about what now is the ratio between the moles, and we should have got the moles of nitrogen along the way as well. We'll finish this out in exam review office hours if you're able to come to that. If not, why don't we start a discussion thread on content on the Blackboard discussion site. Maybe we'll post some pictures of people's work and see if everyone agrees with that approach. All right, thanks for being patient, guys. I'm happy to work through this and many more types of questions today at exam review.